Thank you. Good morning, everybody. My name is Simone Palazzo. I'm from the University of Catania in Italy. The work I'm about to present here is not something that we often see at this conference, but certainly deserves more attention because it deals with the problem of reading the mind and interpreting what we read in order to perform visual object classification. We know that feature extraction from visual content is an essential part in computer vision, and that is what most of its research has gone into in the last years. CNNs have proved to be an efficient and successful model for extracting these kind of features, and one of the reasons for its success is maybe related to the fact that it closely emulates what happens in the human brain. That is, the input signal from the optic nerves go to the different regions in the visual cortex, and each region processes it in more and more complex ways, and then has strong feed-forward connections to the other regions, which are called V1, V2, V3, and so on. However, there is something that the human mind does, the human brain does, but that CNNs do not or cannot. And that's the fact that object categorization in humans is strongly related to a set of cognitive processes which happen on a completely different part of the brain and that are not currently accessible by methods which only perform visual analysis. So the objective of this work is to exploit both the visual and the cognitive information of the brain activity in order to perform visual classification. To do that, we try to directly learn a feature space from the brain activity patterns that we can get by recording EEG from subjects. There is evidence already that brain activity information in EEG recordings contain data related to the visual object classification. So we build upon this evidence for our method. So the first thing we needed was data, of course. We set up an experiment with neuroscientists from the Catania University Hospital. So we asked 6 subjects to look at pictures on a computer screen while we were recording the EEG signals. The images were taken from 40 ImageNet classes. Each image was shown for 500 milliseconds, and we recorded the EEG information using a 128-channel EEG with 1 kilohertz sampling rate and 16-bit resolution per sample. We filtered the signal in order to keep only the beta and gamma bands, which are apparently the most relevant for analyzing this kind of processes. The dataset is publicly available and can be downloaded from our website. These are examples from the classes that we chose for the experiment. So the first thing we did was to use the EEG signals, the raw EEG signals that we got from the data acquisition, process it through a recurrent model. We used LSTMs, and project the features, the temporal sequence, into a feature space where hopefully features would be extracted which are significant and discriminant for visual classification. So the features extracted from the LSTMs were then fed to a classifier, to a simple softmax classifier. After that, in order to apply the same feature space and the same classifier to images which do not have EEG data available, we trained a regressor from input images to the target feature space using a regressor, so that from the input image you can then just use the same model that we trained on the previous stage. There is not a lot of literature on this kind of problem. The main work that we used as a baseline was the one by Kaneshiro et al. It employs SVMs on a very small data set of just 12, it's actually 70 images, so it's very small. And it includes 12 image classes and achieves 29% accuracy. We tested different architectures for encoding our EEG features. The first one is this one. It consists of a sequence of stacked LSTM layers, which take as input the whole set of channels. So this is why we call it common, because the LSTM is shared by all input channels and extract features. Another architecture employs separate LSTMs for each channel, and then they all go to another bigger and common LSTM. Then we tried another architecture with a single LSTM layer and a regular nonlinear output layer from which we extracted the feature vectors. The architecture for feature regression from images was made up of a feature extractor, just a pre-trained CNN, and a regression layer from which we get the output representation. So the results we obtained from the classification on the brain signals directly are shown here. We tested the 3 architectures and used different configurations in terms of number of layers and number of neurons per layer. We computed the test accuracy at the maximum validation accuracy, and what we found out is that this is the common plus the output nonlinear layer is the one that achieved the highest performance, which is a bit more than 80%, which is a great step forward compared to the 29% that were obtained in the previous work. We also investigated something about the importance of the different parts of the signals for classification purposes. We know from the medical literature that in the first 120 milliseconds from the visual stimuli, the human brain performs the feature extraction. It's not clear because it mainly involves cognitive processes which are largely unknown at the moment. What happens after the 120 milliseconds? What we found is that the most important information to perform the classification is actually included in the latter part of the signal. Of course, this is just experimental evidence. This needs to be validated by physiological studies, but it can be a useful insight and a useful starting point. We then tested our regressor and evaluated its accuracy. We computed the mean square error on the regressed EEG features. One of the things we had to deal with was the fact that for each image, we had several EEG features, one for each subject who underwent the experiment. So in order to have just a single regression target for each image, we computed the average of those features, which is common practice in general for EEG processing. We tested different encoders, different feature extractors, so AlexNet, GoogleNet, and VGG, and different regression algorithms, KNN, ridge regression, and random forest. And we found that the GoogleNet plus KNN configuration was the one which achieved the best results and was the one which we employed then for regressing the features. Another thing we did was to test the generalization capabilities of our model, of our features, the EEG features we extracted from our image regressor. So we trained different SVMs using features extracted from GoogleNet, VGG, and our methods. The SVMs were trained on a subset of classes from Caltech 101, which had not been previously used to train our model. What we found is that we achieved a pretty good accuracy at the level of the state-of-the-art, which demonstrated that the features, the EEG features we extracted from the signals, from the EEG signals, were not strictly specific to the training classes that we used, but can be generalized to other classes as well. Yeah, these are some samples from the Caltech classes we used for this test. To conclude, in this work, we demonstrated that we can extract significant features from EEG data that can be used to perform visual classification. And we also found a way to perform that using on images for which we do not have the EEG signals available. As future work, we mean to increase the number of classes and of images, which is one of the main limitations, and it's related to the fact that the more classes and the more images you employ, it means that the longer the experiment takes on the subject. And the longer it takes, the more the subject gets bored or gets distracted, and so the more noise it gets in the data. Another thing we aim to achieve is to try and reverse this process. For what we did was go from EEG signals to visual features, but now it would be interesting to find out what information in the EEG signals is associated to specific visual features. So this can be useful, for example, to uncover some of the mechanisms which happen in our brain and which are not related to visual processing in itself. Another line of work would be that of generating the images from the brain signals. We did some experimental analysis and have some preliminary results on this, and a paper was accepted to ICCV, to next ICCV, where we will present these results. Okay, thank you for your attention.